We all know the equation for the graph of a line in a two-dimensional plane, y equals the slope times x plus the y-intercept. If we restrict our line such that it passes through the origin, the equation is simply y equals a constant times x. This is the graph of a function that has two interesting properties. 1. The output of the sum of inputs is the same as the sum of the outputs of each input, and 2. Scaling the input before applying the function gives the same result as scaling the output after applying the function. This works when both the domain and codomain are the real numbers, but having the same scalar times variable form, we can construct multivariable functions too with the same properties. The graph of which is also geometrically linear or flat, but it would be higher dimensional like a plane in 3D space. We can generalize that linearity property by defining a linear map as a mapping between two sets, a domain and a codomain, that has the same two properties, so the inputs and the outputs of the linear function, or the linear map, do not have to be numbers anymore. Linear maps act on sets of elements called vectors, and a set of vectors is called a vector space. Vectors are simply elements that can be added together or scaled by scalars, so vectors can be anything from arrows, lists, or even single-valued functions themselves. A set of functions that are treated as vectors is called a function space. Functions can be considered as vectors because they can be added together and scaled by scalars. So we can define maps that operate on functions. One example of a map between two function spaces is differentiation. It takes one function as an input and spits out its derivative function. But differentiation is not just a map between function spaces, it's a linear one, because it also preserves the operations of vector addition and scalar multiplication. We call the differentiation operator a linear operator, and we can construct other linear operators using the differentiation operator, linear maps that operate on functions. These are called linear differential operators, and are defined as a function of the differentiation operator. The order of a linear differential operator is the highest order of a derivative that occurs in it. Linear differential operators allow for the compact writing of linear differential equations, equations that relate an unknown function and its derivatives in a linear way. A homogeneous linear differential equation is an equation where one asks, what function does the linear operator map to the zero function? Or in other words, what is the kernel of the linear differential operator? The kernel of a linear map is the set of vectors in the domain that gets mapped to the zero vector in the codomain. The domain in our case is the set of all n times differentiable functions on an interval I, and the codomain is the set of all continuous functions on the same interval. A set of vectors is called linearly independent if one can't be written as a linear combination in terms of the others. The linear independence of a set of functions can be settled somewhat mechanically, using a determinant named after the Polish mathematician Józef Maria Wronski. This determinant is called the Wronskian, and a set of functions is linearly independent when their Wronskian is non-zero. Mathematicians have found that the general solution to a homogeneous linear differential equation of order n can be written as a linear combination of n linearly independent solutions of the linear differential equation. In the language of linear algebra, the kernel of a linear differential operator of order n is n-dimensional. In other words, n linearly independent vectors span the kernel. To recap everything said, let's solve an example of a homogeneous linear differential equation. We first start by writing the equation in the form of a linear differential operator acting on the unknown function y. To find the kernel of this operator, let's assume that the solution has the form of an exponential function with a variable coefficient in the exponent. Because the exponential function is never zero, we get a polynomial in the variable coefficient in the exponent. Solving this polynomial gives us two solutions, either 2 or 3. This means that the two exponential functions associated with these values are solutions to the differential equation. Using the Wronskian, we can easily show that these two exponential functions are linearly independent. And just like that, we have found every single solution to this equation. It is simply any linear combination of the two basis functions. In conclusion, linear differential equations are those which can be reduced to the form L y equals b, where L is some linear operator. Whether it's modeling population growth, electrical circuits, or mechanical systems, linear differential equations provide a powerful tool in our mathematical toolkit. Keep exploring the fascinating world of mathematics.